All right, so good morning, everybody. My name is Jesse, and I'm with Exploring by the Seat of Your Pants. If you're joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And today is a very exciting day. We're dealing with Bats in Parks Canada. We're meeting astronauts talking about moon expeditions that they're planning for. But we are kicking off the festivities with one of my very favorite speakers, Dr. Erica Caden. So she is a particle physicist working in Sudbury, Ontario, Canada, and she gets to go into one of the most elite and amazing research labs on this planet, SNOLAB. So we're going to learn a little bit about it, and specifically, we're going to dive in on dark matter today as a topic, something of keen interest to a lot of our students, because it is Dark Matter Day. Yay, everybody! So we're going to learn a little bit more about it, some of the amazing events that SNOLAB and others around the world are doing to take part. And without further ado, thank you so much for joining us today, Dr. Caden, and take us away.
Thanks for having me, Jesse. And yes, it's Dark Matter Day. All of October is Dark Matter Month, but we really ramp up as we get to Halloween. Yeah, I am a research scientist at SNOLAB. Here is what a scientist looks like. That is an actual wrench that we use to actually adjust a detector. And there are many different things that a scientist does. But we're not here today to talk about me doing science. We're here to talk about dark matter. What is dark matter? We still don't know, which is one of the exciting things and why we're here to talk about it. That we know that dark matter holds galaxies together. So the stars at the edge of this galaxy should be spinning off into space because they're far away from the center of the galaxy where most of the mass is. But the dark matter is holding the galaxy together. The stars aren't spinning off into space. They're staying close together. So you can think of this like in individual galaxies and in big galaxy clusters too. So dark matter is kind of like this invisible space glue. It's kind of like if you're on the merry-go-round and you spin it really fast and you feel like you're going to fly off, the dark matter is like your muscles holding on super tight to the railings. You can also see the effects of dark matter bending light. When we look at a galaxy straight on, it looks round like this, kind of like a cinnamon bun. If you look at a galaxy edge on, it looks like a line. But if you look at the galaxies in the middle here, we know that there is a dark matter distribution between some of these galaxies and us because it bends the light. So it makes these lines into curves and it kind of looks like a smiley face. So this is the effects of dark matter. So we can see how it has interacted with light and the space. So where we study dark matter is at SNOLAB. So luckily it doesn't look quite like this yet. It's a pretty mild October here in Northern Ontario. So yeah, we're at this purple pin kind of above Georgian Bay. So the heart of SNOLAB isn't that building that I showed you. It's actually 2 kilometers underground. So that is like 4 CN towers deep in this active nickel mine. We're in Caden mine, which has been extracting nickel ore from the earth for over 100 years. So all of this red area is the ore body of the nickel ore, and it's nickel and copper and some other heavy metals. But we stay far away from the mining and keep in our own little area of the lab, far from this ore of SNOLAB. So why are we 2 kilometers underground? Why do we need to be so deep? So this video can show why. So there are particles produced in our atmosphere that would make lots of interactions. These are called cosmic rays, and they interact in different layers of the atmosphere. There's the ISS, and produce lots and lots of particles. So we use these 2 kilometers of Earth to shield out these particles. You don't see them interacting as much. So then we have our lab deep underground, and sometimes the particles just fly through and don't interact. Sometimes they do. The particles that we want to see, the dark matter and neutrinos, which are the other things that I study, do interact inside our detectors, and they're not stopped by the 2 kilometers of Earth. But they do stop all of the backgrounds, which we don't want to see in our detectors. Really, the best way to see SNOLAB is to come on a tour. but that's very difficult in these times right now. And even in normal times, it's not easy to get underground. So I can take you on a photo tour. So once we get 2 kilometers underground in the cage, through the cage, we then walk through what's called the drift, which are the hallways in the mines. Then we get to the entrance of the lab. Here we would wash all the dirt off our boots. We are a clean lab, which means not just that the space is clean, is that we have to work and clean ourselves. So here is where our first step in cleanliness is washing the dirt off our boots. Then we take a shower to wash any of the dirt off ourselves. So we have to fully shower every time you go underground, wash your hair with soap, and change into all clean clothes, clean coveralls, clean boots, clean hard hats, like the clothes that I'm in the first pictures. And then we would grab a coffee and have some lunch. In the before times, we could all crowd into the lunchroom here. It's a little bit different now, but this is you wouldn't look to see this and think that we're deep underground. So one of the effects of being deep 2 kilometers underground means there's 30% more atmospheric pressure. So this Pringles can is sealed. You can see that this has been unopened, but the pressure has crunched it in. So all of our detectors, all of our equipment has to be able to withstand this higher air pressure. One of the other nice features of the lab is we have the deepest flush toilets in the world. So you don't have like porta pots and things like that. And these 2 pictures were taken by exploring by the seat of your pants friend, George Karunas, who came down in the lab. So it is a very well lit underground. You don't feel like you're in some deep, dark mining basement. We have well lit hallways and well powered experiments. Everything is very clean. So SNOLAB looks a little bit like a shopping mall with all of the hallways. In the beginning, they were all very empty like this, but now they're filled with different experiments and different parts to build all the experiments themselves. So everything that comes into SNOLAB needs to be cleaned the way that we cleaned ourselves, which means we need a lot of parts ready and already cleaned when we're going to build things. So there's lots of storage space in the lab. So this map kind of shows a layout of the lab and the 3 big caverns, 1, 2, and 3, where we have big experiments. And there's many different smaller experiments in all of these hallways here. So all of the projects here that have a black outline are looking for dark matter. And most of these experiments are looking to see the effect of when a dark matter particle hits and shakes up inside the detector. So it will either make a little bit of light or make a little bit of sound or add a little bit of energy in the form of heat to a detector. And this is how we see the effect of dark matter, hopefully, inside our detectors. So here's another video of the Deep 3600 detector and an animation of what it would look like if with particle interactions. So we're kind of removing different layers, structural floors, that's the tank. Oh, and here is a muon particle hitting inside the detector, but that's not dark matter we're looking for. That just produces light on the outside. The dark matter that we're looking for produces light on the inside, and we can see those light with all of our light detectors. So this little flash of light is our dark matter signal. So this is what we design our detectors to see. So what exactly are we looking for with dark matter? Where is it in our parameter space and what we're able to see in our detectors? So we can plot how big or really how heavy the dark matter particle is versus its likelihood to interact in our detector, or we can maybe call it the catchability. How well can we catch or see its interaction inside our detector? So this gray area is where we have already looked for dark matter. And if the dark matter had a certain amount of catchability or a certain amount of weight, we would be able to see it then. But we haven't. So this is all area that we have excluded. This red area is where our experiments are currently looking. And like I said, we have many, many different experiments that are looking in different catchability ranges and different size ranges. So this is where we're looking, where we're hoping to find dark matter. And this white area is where we are still designing new experiments to study. So we have to maybe come up with new detectors, better ways of cleaning materials, and maybe just have new ideas of what dark matter particles interactions could be. So different catchability measurements. So this is the future. This is where you can contribute someday. So I've talked about dark matter. I've talked about how we're looking at it. But what's really fun is the pictures of the detectors. So this is the Pico experiment, which is using a superheated refrigerator fluid to look for dark matter to produce a tiny bubble if it hits inside the detector. These are pictures of the Cute and Super CDMS detectors. They are using ultra cold germanium crystals. So they're looking for a dark matter particle to come in and knock the nucleus of this germanium atoms that the crystals are made up of, and to see a little flash of electricity from that. Damic and Sensei are this one is Damic and this one is Sensei, are dark matter detectors made from super sensitive digital camera sensors. So they're the same device that's inside everybody's cell phone cameras are the same kind of device that they're using, but they use bigger ones that are ultra clean to look for a dark matter particle kind of interacting inside those detectors. And Deep 3600 uses, which is what we saw in the animation, uses liquid argon. So they're looking for the dark matter particle to bounce off the nucleus of liquid argon and make a little bit of light, just like we saw in the animation. And News G is using gaseous argon doped with methane or neon doped with methane to look for the dark matter particle to produce a little bit of electron scintillation. So we have many, many different experiments looking with all different ways for how to find dark matter. So we know that, I hope I have explained to you that dark matter is all around us. It's in galaxies holding stars together. It's in galaxy clusters. It is just the invisible space glue. And we don't know yet exactly what dark matter is. We think it's a particle. That would make sense in our framework of how we understand the world. But there are many experiments that are looking for dark matter in lots of different ways. They're looking to make it in the big accelerators. They're looking for the evidence of it being interacting in stars in experiment that's on the International Space Station. And we are looking for, at SNOLAB, for ways that dark matter would hit and kind of shake the detectors that we have here. So we are one of the leaders in the global search for dark matter. We have many detectors looking for many different ways. So if you have more questions about dark matter or a dark matter day, you can find us on all the socials at SNOLAB Science.
Fantastic. Dr. Caden, what a fun presentation as always. And I love the imagery. Whoever did all the job to make dark matter look so friendly did a fantastic job. So kudos to them. If you want to come out of screen share, see me again, have a bit of a conversation, great. For any of our folks possibly tuning in on YouTube, if you guys want to share questions in the chat bar, please do. But what I want to do is dive in with some myself. So one of the questions we always get about dark matter, you talk about it being all over the place, it's throughout the universe, it's the glue that holds everything together. Is it around me right now? I mean, I know we don't know what it is, but is the idea that like it's in this room and we just don't have a way of measuring it, or is it more on a galactic scale? Can you explain a little more about that?
Yeah, so that's exactly it. We think we are flying through a field of dark matter all the time. So some dark matter detectors are looking for if the dark matter is here and we're flying through it, or if we're kind of moving with it half of the year, then when we're on the other side of the sun, we're moving against it, we can maybe look for a variation on one side of the year to the other in the rate of dark matter. That's one idea of how to detect it. But yeah, we think we're moving through it all the time, and we just haven't found a way to catch it. So this catchability, it doesn't like to interact with a lot. So this is the challenge.
So I have to ask this question. I've heard it phrased in books before, and I have to field it to you. And that is like, how do we know that our understanding of physics just isn't really, really wrong? Like at this point, are we convinced totally as a scientific community that this is something that is potentially measurable, that we can really, we will eventually pin down? Or is it something where, I don't know, it could be entirely our whole understanding of how the physical universe works could be based on something that might not be accurate, leading us to, bring in this idea of dark matter into play?
So that is a really, really great question. The models that show that we should have dark matter also predict lots of other things in our universe that we do see. So it's, if this like equation gives 90% of things right, and it also predicts this 10% of stuff that we just haven't found yet, it's a pretty good model. So we're just going to keep looking to verify that last 10%. Is it possible that there are models that we don't have yet, that we haven't developed or figured out yet, that also explain everything? That's possible, but we don't have any of those models. We don't have any of those ideas that explain everything, that also give verifiable predictions that we can then test. So there are many models for dark matter. So we're just looking for one kind called WIMPs at SNOLAB. There's a whole other category of dark matter particles called axions that are being looked for in other experiments in other labs, and that could be right too. Considering we've been looking for this for so long and we don't have the answer yet, it can be a little disheartening. So this is one of the nice things, the interplay between experimentalists and theorists, is they come up with the ideas and then we build the detectors to test them. And then we feed back into their theories with our data. So they change their theories. Everything is very iterative and it takes a long time.
Okay, so one of the, I'm going to reference books again. For me, the 4% universe is something that I think a lot of people have heard when it comes to dark matter. And so 4% represents all the matter that we know, all the stars, planets, everything that we know and love in the universe, makes it this small fraction. Dark matter makes up a pretty substantial rest of the chunk, but the rest of it, we hypothesize something called dark energy. So I know we're focusing on dark matter today, but could you explain a little bit as easily as possible what dark energy is? No pressure.
Yes, so I will back up a bit and confirm what you said. Yes, the matter, everything that we see when we look out in the sky, all of the stars, all of the galaxies, and the other planets, are that is about 1/5 of what is the matter, what is the stuff that takes up space and has weight that is out there. So there's 5 times more dark matter than visible matter. So really, the visible matter should be the weird stuff, and the dark matter is the normal stuff, if you think about it that way. But the rest of the stuff, the dark energy, that is what is causing the universe to expand. And that is, if you look at the whole energy construct, what is everything? Like 75% is dark energy, and then 20%-ish is dark matter, and then 5% is regular matter. So there are a whole other group of experiments looking for this dark energy and trying to understand what that is. So in general, all of experimental physics is a really wide open field that you should definitely look into going into if this stuff interests you.
It's so cool. I mean, it's so beyond the realm of our typical everyday understanding of the universe, which makes it really unique as a research problem and something that attracts some of the top scientists in the world for many generations now. And so lucky you for getting to play around in such a neat field with so much to discover. You highlighted so beautifully why SNOLAB is such a special place. Are there other places like SNOLAB around the world, and have you had the chance to go and visit them in person? Could you speak to where they might be, or how many, or if there's any at all? Maybe SNOLAB is entirely unique on the planet. I don't know. Tell me.
So there are many labs around the world that are looking for dark matter, and doing other topics in particle astrophysics. Um, uh, SNOLAB is the only one in Canada, though, that is underground and doing this kind of science. There are a few in the States, one in South Dakota, one in New Mexico. There is one in the UK, Bulby Lab. There's a new one in Australia. There are some that instead of going straight underground, they go underneath mountains. So most of them are in mines, either active mines or former mines. But some go straight underground and some mines are underneath mountains. So there's one in Japan, one in Italy, one in France, and one in China that are all underneath mountains. So they still have the space on top is from mountain coverage instead of going deep underground. But they are all hosts of labs that are looking for dark matter and neutrino research as well. So there's a number of places that you can go to do this research. I just really like Canada.
Very, very. I like Canada too. It's a great place. I know we have an American audience today, but I must say I'm pretty biased.
And I am American, but I came to Canada to do this.
I forgot. I'm sorry. There you go. See, you are our ultimate expat supporter of the fantastic nature of our lovely country. You know, I could start singing the national anthem, but I'll spare everybody that fate. So to get into a career like yours, how do you go about that? I mean, if we have students joining today, anywhere from grade 6 through grade 12, if they wanted to finish up and end up like you, what was your journey and sort of what might be the other options available for people if they wanted to end up in this field broadly?
So I wasn't sure of what I wanted to do when I was that age, grade 6 to even kind of my first year in university. I liked science. I liked knowing things. I liked figuring things out. So as I kind of got on in school, I really enjoyed math class. I enjoyed science classes, and I really enjoyed chemistry and physics. And I thought engineering was really interesting in the idea of building things. So when I then was in undergrad, I really enjoyed physics as this explains everything. This is the one way to answer all the questions. Of course, now we know that there's just many, many, many more questions, but young me thought this was the answer. So I majored in physics in undergrad, and then I went on to continue studying physics in grad school. And I worked on an experiment that was in France when my school was in Philadelphia, and loved the experience of being on site, working on a detector, working with a large team, international team of people, all working to build this one device to answer big questions, to understand more about the world around us. And that's where I first really got into neutrinos and started hearing about dark matter, and kept on doing that. Moved from Philadelphia to Canada to do a postdoc at Laurentian University, and then got a job as a research scientist at SNOLAB, and get to talk about it now, which is one of the other things I really like about science, is telling people about how cool science is.
We can certainly tell that. Now, I mean, we've asked this question, and every time you've had one of these broadcasts with us and you've been so generous with your time, you've done, I think, geez, we might even be over 10 now in sessions over the last 5 years, and thank you so much for that. Is there a favorite part of your job? I mean, you seem to love absolutely all of it. Is there a favorite part? And actually, since you're so enthusiastic, is there a least favorite part? Or is there a drawback to doing some of this work? I mean, like, let's put on your pessimism hat for a minute when you're done with the good parts, and tell us for some folks that might want to end up in this career what some of the perks and drawbacks are.
So I'll actually start with the drawbacks, is that it can be hard when you're trying to figure out the questions and answer the questions that we don't have answers to yet. It can be really difficult when you're writing computer code and you're getting stuck and it's getting really frustrating, and you can't understand the problems and you're not even sure if you're asking the right questions. It can be really demoralizing at times. And really everything is hard right now when we are doing school from home or working remotely. This is not my office at the lab. This is my home. Not having the interactions with other people can be, for some people, really difficult. So one of the things that I like most about my science is that it is collaborative, that we have big groups of people working on these projects and working together. So when you have difficult questions, or even when you have what you think are stupid questions, there are people to go and ask them to. So, right, like the being in COVID times now, not being down the hall from people can be very difficult. Um, or sometimes trying to formulate the question, even when you are next to people, the uncertainty in, is this a stupid question? Am I going down the wrong path? That can be demoralizing and difficult. That's one of the difficult things. Sometimes looking around and not feeling like you don't belong, that there's no one here that looks like you, that can be very difficult. So one of the things that I try to do as a group leader and in talking here is to show people that there are scientists who look like you, that you belong in this field, and that we need you and your ideas too. So to try to figure out how to not be demoralized when there's no one who looks like you, or to not think that your question is stupid, and to just keep on pushing on, taking breaks when you need, but to know that you belong here too. That is one of the best things about my job, is that I get to help reinforce that idea.
What a beautiful message, Erica. I love that answer. That's awesome. You know what? I wanted, that would be a perfect place to end the broadcast, actually. But I do want to highlight for folks that are tuning in, what's next in dark matter research. I mean, you highlighted some of the current state of things, showcased these amazing experiments. What are we trying next? When are we trying it? Is there anything big to look out for that's exciting for folks that are tuning in from home that are keen on dark matter?
Yeah, so keep paying attention to SNOLAB and this weekend with Dark Matter Day, with what more presentations and especially some funny tweets from the dark matter particle. He tends to take over our Twitter feed right around this time of year, and he is snarky. He will tell you all about the how silly we are for what we're trying, or how he's still hiding from us. We have one of the really fun things about SNOLAB is that our experiments are constantly under construction. As soon as we have one project built, we're moving to the next one, because that one's taking data and doing science. We're building our next ideas. And that's true in most of science too. You have this idea and you start to build it, but that just from practical limitations, where your limits will be. And you can now start to think of how to build the next generation of detector and go beyond those limits. So some of the experiments that I showed are currently running, and some of them are still just ideas and under construction right now. So we are always looking to push into that white area of the plot, where are we going next? How do we catch smaller and smaller dark matter particles? How do we get the best data to give the theorists to make new theories on where we should look next? How do we design detectors that are cleaner so we can improve the catchability? To press down in their interaction likelihood. There is so much to do still. And maybe we'll be lucky. Maybe we'll find dark matter, and then we can build more experiments that are sensitive in that area to try and understand more of the properties of dark matter, which is what we need to do after we find it.
Erica, with people as passionate and brilliant as you on the case, I have no doubt you'll get some major headlines in the not too distant future. I'm always excited to get the chance to chat with you. And again, our audience of students from all around the world loves hearing about these really amazing cutting edge research. So kudos to you, and have fun with Dark Matter Day and Dark Matter Month and all of it. I did want to highlight, you showcased a few things throughout the broadcast. SNOLAB Science, if you want to learn more, SNOLAB does it better than pretty much anyone in highlighting their research. And if Dark Matter takes over the feed, I don't know, it might get a little crazy, but I encourage everyone to check that out and have some fun. darkmatterday.com, events all over the place. Do check that out if you're keen on dark matter. Even if you're not keen on dark matter, check it out. You'll find out some really cool stuff. And of course, SNOLAB's website, a little bit big. We didn't quite make it a 2-bar thing, but you can check out SNOLAB's efforts to celebrate Dark Matter Day with this program as a kickoff, and with other events happening throughout the afternoon. So Erica, thank you so much for joining us. I really appreciate you taking the time today.
Thanks for the opportunity, Jesse.
Awesome. Have a wonderful day and keep up the